ethyl ethanoate and water. It forms ethanoic acid and ethanol. Right, in the question told you start with 1 mole of ethyl ethanoate, and at the point of equilibrium you have 0.3 moles. I'll write that down here, 0.3 moles of ethanoic acid. Right, first we'll start off by writing the Kc expression for the reaction. To write that, all you do is very simply take a new piece of paper. Let's see what we're doing over here. I'm going to write Kc equals, at the top in square brackets, the products, ethanoic acid and ethanol. For those people who don't do A-level maths, there is no mathematical operation written between the two square brackets, so that means times. Underneath it we have our reactants, ethyl ethanoate and water. Okay, now the problem is we know the concentration of ethanoic acid. And what we have to think about is, if we take the molecule over here of ethyl ethanoate, it will snap into 2 products. 1 molecule of ethyl ethanoate will break into 1 molecule of ethanoic acid and 1 molecule of ethanol. So if I've got 0.3 moles of ethanoic acid, I'm going to get 0.3 moles of ethanol. Okay, but here we have a problem. We don't have 1 mole of ethyl ethanoate, we've actually used up 0.3 moles. So this, the concentration of ethyl ethanoate is 0.7. Right, we can also say that if we started off with 1 mole of water, we'd end up with 0.7 moles of water as well. All we now need to do is substitute these numbers into the Kc expression. So we'll end up with Kc equals, here, 0.3, the concentration of ethanoic acid multiplied by the concentration of ethanol divided by the concentration of ethyl ethanoate multiplied by the concentration of water in moles as 0.7. And we put all of that into our calculation, we get a value of Kc is equal to 0.184. Now, I really am not concerned with the volumes at the end, because we can see if we had volume of ethanoic acid and volume of ethanol, underneath that the volume of ethyl ethanoate and the volume of water, these would, in the old terms that we use, cancel each other out. In other words, volume divided by volume is 1, volume divided by volume is 1, so multiplying anything by 1 or dividing by 1 doesn't really change anything. In other words, if I times my top by 2, divide it by 2, I'm not doing anything at all. So why do it? And we don't have to do anything to it, so our answer, the Kc, is 0.184. That is how to work out Kc for a very simple equilibrium. Okay, let's tinker on a tough one. B is an equilibrium and forms 2 Cs. These are an aqueous solution. Alright, let's make this one trickier. You have placed 4 moles of B in 20 litres or dm cubed of water. So you've made it up to 20 dm cubed. B, oh, we don't know, we leave it sealed up in this large 20 litre container, and at the end of it what we find is we have 1.5 moles of B left in the container. Alright, so let's see what we've got. A couple of places where people can make mistakes. Let's first of all get a Kc expression out. Well, I'm going to write that here. Kc is equal to C in square brackets squared over B in square brackets. Okay, now let's have a look at what we've got. We've got 1.5 moles of B. And what people would think is, well, okay, I've got 1.5 moles of B, well, I must have 1.5 moles of C. Well, actually, no. Each molecule of B breaks up into 2 molecules of C. So we've got 2 times that many moles of C. So we've actually made 3 moles of C. So at the end, well, the point of equilibrium, we've got 1.5 moles of B and 3 moles of C. Now, this is all in a 20 litres, made up to 20 litres. So before we can use the Kc expression, we must convert these, because we've got 2, or a squared function at the top and a single function at the bottom, so they don't cancel each other out. So volume is quite important in this. So we must work out the moles per litre. Now, to work out the moles per litre of B, what you do is you take 1.5, divide it by our volume in dm cubed, 20. And 1.5 divided by 20 should give us a really interesting number, like 0.0750. We do the same with B, but instead of 1.5, we have, with C, we have 3. We've got 3 moles of C over 20. 3/20ths, which should give us 0.25. Now coming back to our Kc expression, we can now use our Kc expression, which we've wrote right in the centre of my working out there. We can write Kc is equal to C squared, the concentration C, which is 0.25 squared. Let's put in brackets, not mathematically needed, but we substitute is 0.0075. We do 0.25 squared on our calculator, we do 0.0750, and our Kc is equal to 0.833 moles per litre. Okay, alright, the next section looks at working concentrations out when we're given Kc. So, let's put some paper over here. Let's think of some really interesting letters. A and B. Okay, so A is in equilibrium with B, and I'm not really concerned by what it is. All I know is I've got 1 molecule on this side and 1 molecule on that side. They're both liquids. Now, these 2 things are liquid. What we know is we start off with 1 mole of A, and the question says if 1 mole of A is allowed to reach equilibrium, well, how many moles of B will be formed? And let's say Kc has a value of 0.02. It will go on and add on things like at the temperature, the da-da-da, the ra-da-da, but really not interested. All I know is that I have 1 mole of A, my Kc is 0.02, and I need to work out the concentration of B. What not to do. Okay, now we can start with Kc. We write an expression for Kc is equal to the concentration of B, our products on the top, over the concentration of A, our reactants underneath. What we don't do is put a 1 underneath here and think 0.02, therefore 0.02 moles of B are made, and no. We've got to do a little bit of algebra. If you don't like algebra, well, hard luck. There's no real way around it. Okay, so let me explain to you what goes on in my bizarre, strange head of chemistry. Actually, just my bizarre, strange head. Okay, not just chemistry. Life, the universe and everything. The way I see it is, if I've got 1 mole of air, at the end of it, well, I know I'm going to end up with, let's say, X mole. I'm going to use X because we always used X at GCSE maths, and for all those people who are not doing A-level maths, it's nice to be nostalgic and go back to GCSE maths. We have X moles of B. Well, if that's the case, at the point of equilibrium, if I've got X moles of B, I've actually lost X moles of A. The moles of A that turned into B. I want to clarify it. Let's think of it another way. I must lose one molecule of A to make one molecule of B. That is really it. Okay, now let's do some funny algebra. I take my Kc expression. Kc equals the concentration of B over the concentration of A. And I substitute this time for my terms. Kc is equal to concentration of B, which is X, over concentration of A at the point when equilibrium was achieved, 1 minus X. Well, we know what Kc is. Kc is 0. Write it over here, 0.02. Given to us in the question. 1 minus X. Now here comes a lovely, lovely algebraic bit. So make some more room, some more paper so I can see what I'm going to do. This is divided by 1 minus X. There's two ways of looking at this. The float and ping method, which is taught in GCSE Maths, which is, this is a divide, you take it across there, it becomes a times, to give us 0.02, and I put it in brackets, times 1 minus X equals X. And X is what we're trying to find. The other way of looking at it is, if I'm dividing this side by 1 minus X, I can multiply the side by 1 minus X to get rid of it, then I must multiply that side by 1 minus X. Whichever way you were taught is fine. There's probably another whole host of methodologies. Now if I expand this bracket, I end up with 1 times 0.02, which is 0.02, minus 0.02x, and that's all equal to x. Oh, now it gets strange. I've got an x on this side, an x on that side, and I don't like it. This is a minus x, so I must move it across here. Again, depending on how you think, the float and ping, the minus moves across, therefore it becomes a plus. Algebra, being to balance, either add 0.02x on this side to get rid of it, I must add 0.02x to that side. 0.02 equals x, add 0.02x. For all those who do A-level maths will now be going absolutely spare and insane, saying hurry up. Well, bear with me. 1x, and that's all we have there, add 0.02 is 1.02x. Wow. At this point here, I want x. I want x all by itself, so I divide this by 1.02. I divide this by 1.02, and what we should get is a concentration of B. So the concentration of B, and I put it in square brackets here, should be 0.0196 moles. Excellent. So in this one, we've got a reaction, an equilibrium reaction of 2P going to S and T. We know we start with 1 mole of P, and Kc is 36. And we need to find the number of moles of S and T. So let's start with writing out the Kc expression. Kc would be equal to concentration of S over the times concentration of T over the concentration of P squared. Okay, now we can do what we did before, which is change this or express it in an algebraic way. So if you have 2P in equilibrium to S and T, and we start with 1 mole of P, well, you must end up with, let's say, F moles of S. Got a little bit of a problem. If I've got F moles of S, I've got F moles of T, and I must have lost F moles of P. The problem is I've got 2 P's. If we look at the ratio, the proportion of S to P's, we have twice as many P's, or in other words, half as many S's. So we can divide each of these by 2. Okay. Now, we would divide them by volume to find concentration, but I'm not going to, because I've got 2 terms at the bottom, although granted this is P squared. This actually means, just to recap, P squared in square bracket is P times P, So as I said before, if you have the same number of terms at the bottom as the top, the volume will cancel itself out. And now I'm going to take this, and knowing that a lot of pupils nowadays don't like fractions, you're not taught fractions, you're taught decimals, you want decimals. What I'm going to do is rewrite this as 0.5f and 0.5f. Okay. So now what I'm going to do is I'm going to take my KC expression and I'm going to substitute into my KC expression these values, which would be 0.5f times 0.5f divided by 1 minus f, and we must square all of it, not just the f. Alright, well, if I look at that, and if I look at how to write that, I see something. And what I see is 0.5f and 0.5f would be multiplied together, so I could rewrite it in a more simpler form. Kc is equal to 0.5f squared over 1 minus f squared. We're told in question, I said at the start, Kc was 36. Now, for all those who are good at maths will realise that 36 is a square number. And if we take our expression, we'll notice what squares are all over the place. And we can square root the entire expression to give 0.5f over 1 minus f. Careful, the square root of 36 has two possible values, either plus 6 or minus 6. Now if you've got this far, well done. If you're not a mathematician, leave it. If you've got this far, that's all you really need to do, because you don't want to spend lots and lots of time solving this. For all those who are mathematicians, well, you don't really need me to explain this bit. If you do, check out the next bit. Okay, so all those who aren't mathematicians, let's pick one. We're going to pick, let's say, plus 6 is equal to 0.5f over 1 minus f. You move the entire 1 minus f here across the other side to give you 6 times 1 minus f equals 0.5f. The 1 minus f is dividing out 0.5f. So as we take it to the side, it becomes a times. I expand this bracket to give me 6 minus 6f equals 0.5f. I then move this minus 6f over, gives me 6 equals, becomes a plus 6f, 6.5f. Divide this by 6.5 and divide this side by 6.5. It gives me an answer of 0.92. I think 0.92. Yes, an answer is 0.92. And that's how to work that out.